Hello. We have learned a lot of theories in asymptotics, and now we are going to start the real estimation theory. So I'll first set up the notation for M estimation, extremum estimation, and remember we started from maximization or minimization. So we assume that you have an identification result which says the true parameter maximizes a function q, and q is referred to as the criterion function q0. I usually use 0 subscript 0 for the true value and hat as its estimator counterpart. So we know that the true parameter maximizes the criterion function. Then our plan is we are going to estimate the criterion function first. Usually the criterion function is not available, so we need to estimate q0 by q hat subscript n. So using n number of samples, we estimate the function, and then you obtain the m estimator by maximizing the estimated criterion function, right? So q hat is the estimated criterion function, and you are going to maximize based on your estimate of the criterion function. And the examples. In the OLS case, beta hat is a minimum. So minimum and maximum are the same depending on whether you take a negative sign or not. So beta hat is obtained by minimizing this guy. So this is a kind of sample mean, 1 over n summation means sample mean of the squared residuals. So squared residual sample mean is the estimated criterion function. And maximum likelihood estimator is obtained by maximizing the average of log likelihood. The log likelihood f is the density function, parameterized density function, and log f is log likelihood function. And so as you can see, in many cases, the criterion function takes the form of sample average of something. So we are going to use this notation. I will use Li. L is, you can think it as a log likelihood function. Log likelihood function's sample average is your estimated criterion function, but the true criterion function is its population mean. So the population mean expected value of log likelihood function is maximized at the true parameter. That is what we have in our setup. Okay, I'm going to show you graphs first. If I had the blackboard, I would use the blackboard, but please understand using simple diagram on PowerPoint. So, like graphically, we have that the identification result tells you that the true parameter theta 0 minimizes q0, criterion function q0. So q0 is like this, and theta 0 is its minimum. This point is the true parameter. You would like to estimate this point where the minimum is, right? And we are going to estimate the parameter by this principle, minimizing. But q0, the criterion function, is not observed. This is purely theoretical existence. And instead, you have an estimator for q. So you estimate the criterion function by a wiggly estimator. So your estimator is q hat, and q hat has estimation errors. The difference between the black line and the red line is the estimation error. So of course the estimation, we believe that the estimation is accurate enough and converges to the true function. And then let's see what you observe in practice is only the red line, red function, q hat. Q0 is never observed, and its minimizer is here, q theta hat n. Theta hat is the minimizer of this estimated criterion function. This is your estimator. If there was a different form of error, then your estimator will be maybe different. So the minimization, so the minimum is here, but true minimum is here. This much difference, the difference between theta 0 and theta hat is coming from the estimation error in q hat. So now we would like to study under what conditions the estimator is consistent, or the difference between these two minimizers approach to 0. I will, to do that, I'm going to show you counterexamples first, when the estimator does not converge to the true parameter. I will show you several, maybe 3, 4 examples. This is the first example. Suppose that your estimator is doing well. You are estimating the criterion function like this, and suddenly its behavior is becoming bad, worse, as theta goes to infinity. So as theta goes to infinity, it goes down somehow for some reason. So in this case, the estimated criterion function has its minimum only at the infinity, right? So because of this, your minimum is always in the infinity, and it will never converge to the true parameter. So you don't know what's going on in this area. So you don't know what's going on in the infinity, and this problem may happen because the parameter space is too wide. It is not bounded. So it may diverge to the infinity. Then that may cause a problem. This is first case, we have a problem. And second case, this is your estimator. Your estimator is converging, but the convergence is not uniform. So the convergence is pretty quick here. It's nice converging rate here, but convergence rate is much slower here. So even n increases, convergence is much slower in this area, so your estimator minimum will be here. This slow convergence causes a big problem. So the convergence is too slow at some point here. So the minimum of this estimated criterion function must be here. And its convergence to the true parameter is not guaranteed if the convergence is too slow. So then this problem is like we discussed the similar problem earlier when we study uniform convergence. The convergence is not uniform. So at some point the convergence is too slow, but at other points it's nice, it's fast. So because of these difference in convergence rates, your estimator may not converge to the true parameter, right? This is another case. And the third case is a problem of the true criterion function. Suppose that the criterion function has a discontinuity here. So it drops here and again goes nice. So it's discontinuous at this point. But the problem here is, at this discontinuous point, it is empty, so still the minimum is here. But this point is very close to the minimum almost the minimum. So theta 1 is not exactly achieving this point, but as it converges to theta 1, as theta converges to theta 1, the value, the function also approaches to the minimum, right? So this minimum is not a dominant, not a clean minimum. So there is a strong alternative candidate which minimizes the criterion function. In this case, your estimator may look like this. Say your estimator can be continuous, but still there is a problem. The problem is coming from the similarity between these 2 points. So because theta 0 and theta 1 have 2 similar function values, small error can change their order. So without error, you know that theta 0 achieves this point, but theta 1 does not. But because of the error, the order, the ranking could be easily flipped. So in this case, your estimator so the minimum will be taken usually here, can be taken here. So in that case, your estimator will converge to theta 1, not theta 0. So if the minimum is coming from here, of course, in the end, it will converge to theta 1, not theta 0. This problem is coming from the discontinuity, of course, but at the same time, the discontinuity causes not a clean minimum problem. So the minimum is not a clean one, so there are 2 similar. So combined with the discontinuity, it may have a bigger problem. So these 3 cases, I hope you understand the intuition behind it, and I will formulate the conditions that rule out these examples. Okay, I'm going to continue in the next video.